Hello everyone, I'm Hayden, the team lead of Cornell Seismic Design. And today I'm joined by Leia, our dynamics lead, Eric, our architecture lead, and Royce, our design lead. And we're super excited to share with you our tower, Perennial. Leia will get us started with the geotech.
Thank you, Hayden. Perennial is located on the Puget-Willamette Fork on the Cascadia subduction zone, where the Juan de Fuca plate subducts beneath the North American plate. The dominant seismic hazard in this region are megathrust earthquakes, the last of which occurred in 1700, where a 9.2 magnitude earthquake ruptured the length of the Cascadia subduction zone. Paleoseismic data estimates a recurrence interval of 500 years. Therefore, our design is built to withstand an event of that magnitude. Additional hazards on nearby crustal fault systems, including the Portland Hills, Hales Creek, and Mount Angel, can generate earthquakes of magnitude 7 or greater on their own. The site consists of sandy and silty soils with deeper layers that are loose, poorly graded, and highly saturated, conditions that are susceptible to liquefaction and lateral spreading. Shear wave velocities at the site range from 240 to 300 meters per second, typically corresponding to site class D. However, the significant liquefaction risk leads us to conservatively classify the site as site class F under ASCE 722. To address these conditions, our design incorporates a pile ground foundation extending to bedrock, along with increased structural stiffness and supplemental damping to reduce seismic demand. Our ground motion selection utilized the NHR3 NGA subduction database. Following the ground motion selection guide, we applied an upper shear wave velocity limit of 300 meters per second to better reflect site conditions. We then used a weighting function to prioritize periods between 0 and 1 second, aligning with the expected dynamic response of our structure in the MCR spectrum. This process generated an initial set of 30 ground motions that were then reduced through visual inspection and mean square error rankings to eliminate records with excessive scaling and poor spectral fit. The final selection consists of 11 ground motions that closely match the target spectrum and provide a representative range of seismic demands for the site. Next, Eric will present the architectural concept.
Thank you, Leia. For years, the Portland Japanese Garden, shown here, and the Portland Nursery have showcased perennial plant communities that have attracted visitors year-round. Perennial takes its name from this tower and showcases these plants embracing their longevity, resilience, and renewal to creating a lasting public place while reflecting Portland's commitment to ecological sustainability. To start, the ecology drives design. Native species such as the Oregon grape and swordfern are planted throughout the tower's vertical green wall, extending the green loop upward. These plant communities support local biodiversity while creating shaded gathering. Within the tower design, the building expresses its structural rhythm through tree-like mullions that reveal the engineering beneath. The structural frame establishes the facade's language while organizing residential units, circulation, and shared spaces. Sustainability is embedded through integrated environmental systems. Rainwater, shown here, is collected from the roof and facade for irrigation, reducing drinking water demand, and stormwater runoff. Vertical vegetation links the rooftop and facade for communal spaces, lowering surface temperatures and reducing cooling loads. Roof gardens provide additional shading while creating accessible outdoor spaces. Passive strategies guided by solar form binding maximize daylighting and natural ventilation, further reducing energy consumption. The program is organized around a sequence of public and private spaces. A welcoming ground floor lobby opens onto a landscape garden while residential units rise above the space, connected by greenery. At the ground level, gently sloped ramps provide equitable access to all areas. In accordance to the ADA principles and the 2021 International Building Code, a centralized core houses elevators and protected stairways, providing continuous circulation from the street level to the rooftop. Following an earthquake, occupants can safely evacuate through protected routes to designated assembly areas. Shown in our Zone 1 and Zone 2 floor plans, the design takes into account to public and private circulation. Within our Zone 3 and Zone 4, the red lines and blue lines are annotated as public and private circulation, where residents can freely access their units and the public to the rooftop and garden terraces. At its heart, the building reflects Portland's identity by integrating native ecology, structural honesty, environmental systems with inclusive circulation. Thank you. Now Royce will talk about the design.
Thank you, Eric. A preliminary dynamic analysis of the tower geometry showed that the diagonal symmetry of the tower results in two orthogonal bending modes oriented 45 degrees from the directions of shaking. These results were also validated through the use of SAP 2000 analysis. To address the resulting stresses as efficiently as possible, the tower's main structural system consists of diagonally braced walls oriented along these axes, stiffening it in these directions. These walls, originating in Zone 1 and continuing through Zone 2, form the core of the tower's structural system. In the initial tower design, the core featured sparser bracing along this wall, attached to 3 orthogonal walls. However, both SAP 2000 analysis and real-life testing indicated a need for more densely braced columns near the edges of this long face, sparser bracing in the orthogonal direction, and another parallel face. The buildable area of Zone 3, which overhangs the non-buildable area of Zone 1, presents 2 major challenges. First, the asymmetric loading of Zone 3 causes torsion due to a misalignment of the center of stiffness and center of mass. To address the resulting stresses, an external frame extends from Zone 3, consisting of long-span diagonals. Second, to address the overturning moment and shear failure due to column discontinuities between Zones 3 and Zones 1, the external frame with long-span diagonals tie in directly from the core, supporting the overhanging columns of Zone 3 directly. In our original design, the 2 Zone 3 towers were braced primarily using internal faces. However, these were susceptible to torsion and did not transfer load efficiently to the lower zones. Instead of internal faces, external diagonals provide direct load paths from Zone 3 down to the lower zones. This framing extends upwards to Zone 4 to support its lone dead load and minimize torsion throughout. To capture the maximum floor area in each zone, a mixture of structural diaphragm floors and non-structural beams are used. The diaphragm floors work in tandem with the external shell, connecting orthogonal faces of the core together to prevent out-of-plane bending. Non-structural beams are used to fill out the rest of the buildable floor area as shown without affecting the structural response. Now Hayden will present the analysis.
Thank you. This year, to analyze our tower, we built a MATLAB program that outputs our tower response to any given ground motion input, specifically tuned to the parameters of perennial. So let's take a closer look at how it works. We started by shaking our tower on the given ground motion 1. We measured the acceleration at the base and the roof and input it into the OKID algorithm, which produced an impulse response function, shown here, that describes our tower's response to any disturbance. We then compared this computed response to an experimental pullback test. You can see the comparison shown here, as well as the tabulated natural frequencies and damping ratios. And while they don't perfectly align, it captures the overall dynamic envelope quite well. Importantly, we also observed 2 natural frequencies corresponding to the 2 orthogonal bending modes predicted in our preliminary analysis, reaffirming our decision to orient the structural walls diagonal to the direction of shake. After verifying the model experimentally, we moved on to converting it into a state space system using the eigensystem realization algorithm. To make our predictions more accurate, we tuned the model in 2 ways. The first, we iterated through model parameters, including Markov parameter length, observer order, and band filter width. And second, we compared the predicted damping ratios, natural frequency, and ground motion response to our measured values. The final model was chosen based on scoring systems emphasizing ground motion 1 response. After tuning the model, we can compare the untuned versus tuned impulse response functions to see how tuning affected the model. We can also compare this to our experimental response and see that the model now much closely matches the experimental results better. Now let's talk full ground motion prediction. For ground motion 1, the model predicted it with 70% accuracy, and for ground motion 2, 50% accuracy. And again, it correctly predicts many of the characteristic responses of our experimental ground motion. We use this model to make our final predictions, shown in this table, and predict a updated final annual building cost of $700,000. Thank you, judges, for your time. Thank you, ERI and SLC, for making this competition such an important part of my college experience. Thank you to our sponsor, CSI, and we'd love to take your questions.